So we will continue now with our program as advertised. We will have a panel discussion on related to what you just saw in the presentation, and the moderator of this panel is somebody who's very close to my heart, like one of the first group of assistant professors I hired when I came in as a head of mechanical engineering. Started in 2020 with us, right in the pandemic, a challenging time, but it's my really distinct pleasure to introduce to you Rebecca Ciez. She is an assistant professor in the School of Mechanical Engineering, but also has a joint appointment with the newly formed School of Sustainability Engineering and Environmental Engineering. Rebecca her research focuses on the intersection of technology, economics, and policy to enable the transition of decarbonized energy system. Prior to Purdue, before she came to us, right, she was a postdoc at the Columbia Electrochemical Energy Center and the Andlinger Center for Energy and the Environment at Princeton University. Dr. Ciez was a negative emission science Skylark Fellow, these are interesting names, and was named a 40 under 40 rising star in environmental engineering and science by the American Academy of Environmental Engineers and Scientists. So it's my distinct pleasure. Rebecca, I will hand it over to you.
All right. Thank you so much. And so we have a distinguished panel of speakers here today. So I want to reintroduce, for those of you who might just be joining us, Dr. Chalamala, who is a professor of material science in engineering and electrical and computer engineering at the University of Texas at Dallas. He very, very recently took this position. He was previously at Sandia as a senior scientist, where he led efforts in grid modernization, energy storage, and power electronics. He has many, many distinguished awards. He's an IEEE, AAAS, MRS, and National Academy of Inventors Fellow, and he serves in many leadership roles in different engineering societies, and most recently he won the IEEE Harry Diamond Award. And so with that, I would like to welcome him to the stage. Yeah, do you want to take me to this one? All right. Next up, we have Professor Vilas, who is a professor of chemical engineering here at Purdue. Prior to joining us here at Purdue, he was an Argonne scholar and material scientist at Argonne National Laboratory. His research contributions span energy materials, sustainability, and chemical process innovation. He's a fellow of the Royal Society of Chemistry, and he's also a Fulbright specialist and a two-time Guinness World Record holder. So maybe you can figure out what the world records are for maybe after the panel. He's been recognized in many different professional capacities, but here at Purdue, he was an outstanding teacher, most impactful inventor, and a faculty scholar honors. So with that, welcome to the stage. All right. Our next panelist is also from Purdue. Professor Junjie Chin is an assistant professor in the Elmore Family School of Electrical and Computer Engineering. Before he joined us at Purdue, he was a postdoctoral researcher at the University of California at Berkeley. He obtained his PhD in computational and mathematical engineering from Stanford, so a little bit of a Bay Area rivalry there. And he received the NSF Career Award in 2023, the Google Research Scholar Award in 2022, and in 2020, the O. Hugo Schuck Best Paper Award from the American Automatic Control Council. So with that, welcome to the stage. And then our final panelist today is D.L. Oates, who's he leads the MISO's Markets and Grid Research Group. So MISO is the Mid-Continent Independent System Operator. So we saw some maps of the different system operators in the United States, and so he represents one of those and their work. So his work contributes to sustaining reliability and increasing value for MISO's customers. He has held electric power-focused positions in academia, consulting, and technology. At the Brattle Group, he supported electricity market operators, utilities, and asset owners to address market design, asset valuation, and regulatory questions. He holds a PhD in engineering and public policy from Carnegie Mellon University and a bachelor's degree in engineering physics from Queen's University in Canada. So with that, welcome. All right, so I guess the first sort of topic to lead us into this is just a little bit of introduction or background, thinking about how the role of energy storage has evolved in the modern grid planning over the past decade or so, and what are the biggest shifts driving adoption today. And so for Professor Chalamala, are batteries being deployed in different locations from where they had previously, and what are the trends that you're seeing in the next few years?
Yeah, I think, can you hear me? Okay. Well, if you look at the batteries, I think, there has been a lot of growth across the board. Behind the meter, significant amount of storage. And on the grid side, as I mentioned earlier, earlier it was mostly regulation market, primarily because there was a market. And now many other applications are opening up. So storage is there everywhere now. And what is limiting storage in some of those new applications is, market mechanisms and also to a certain extent, regulatory practices in many markets.
So Professor Pohl, are there significant shifts? You do a lot of work with battery chemistries. Have the chemistries themselves changed a lot in recent years? Are you seeing some recent trends in what you're expecting for the next couple of decades?
Yeah, so lithium-ion batteries are really popular for everywhere, in your cell phone, laptop, electric vehicles, and also for grid storage. They are the robust backbone for grid storage today. There will be certain change. There is a small shift happening. Flow batteries are coming up, but as Professor Chalamala mentioned that, they're not yet at the scale available. So the shift is happening, but slowly.
Professor Chin, you do a lot of work related to electric vehicle adoption, and so are the trends in EV adoption reinforcing, or are they competing with energy storage? How do you sort of see that market playing out?
Thanks for the question. So, well, I think Dr. Caramana already sort of talked about this in his talk about, the adoption of EV actually pushed the, R&D and the manufacturing. So essentially you see a economy of scale in terms of the battery production, and that's really driven, and that's really beneficial for the grid scale battery as well. So that's really mostly on the supply side of different battery material, battery technology, and so on. But if you also think about the demand side of batteries, you can think about, okay, without a lot of, let's say, coordinated or managed charging programs, this EV charging load potentially can increase the peak load of the grid, and that could lead to additional demand of flexibility in the grid. So that means perhaps we need more grid battery as well. So in both supply and demand side, you're really thinking about these two technology or adoption trend, they are sort of reinforcing each other.
And Dr. Oates, how is MISO thinking about integrating energy storage? How are the trends maybe different from different ISOs in different parts of the country?
Sure, and I'll just maybe take 30 seconds to describe MISO for those who are maybe less familiar with it. So the MISO is one of 7 system operators, wholesale market system operators in the country. We primarily operate the high voltage transmission system. We also administer markets for electricity and have a role in transmission planning. So everything that we see is at that commercial scale already that Babu was giving us a great overview of earlier. We also saw in that presentation that nationwide, something like 30 gigawatts of grid scale storage are what's been deployed, and very little of that has been deployed in MISO. We have about a gigawatt of grid scale storage in our footprint today. But the expectation for that going out to about 2030 is maybe an incremental 10 on top of that looks realistic. It's not 100% certain, but the growth does look like more of a hockey stick driven by a number of factors. So that would put us somewhere comparable to where Texas and California are today, although still a little bit behind. But certainly looks like growth ahead.
Great. And so I guess sort of sticking with that theme, are there big technical and regulatory challenges that we should talk about? And especially sort of in the MISO space, like as you're trying to create market mechanisms to allow for these kind of technologies to be integrated and participate, how are you thinking about those markets and how they evolve for different applications?
Yeah, so we spend a fair bit of time thinking about the market mechanisms and the operational tools and systems that are needed to operate reliably. And most of that infrastructure was designed for dispatchable thermal power plants in mind. So there's a variety of ways that that shows up. And so there are some gaps. I will say that in the last sort of 5 to 10 years, there's been a lot of work to integrate storage into the wholesale markets. So today, energy storage resources can participate in all of our markets. So capacity, energy, and ancillary services, they can sell all of those products. But there are some tricks, particularly at the really short time scale, real-time market scale, where there's some disconnects. There's also some challenges around transmission to serve the load and the charges for that we need to take a look at.
And Professor Chalamala, how does energy storage enhance sort of grid flexibility in systems with high renewable penetration, and what can we learn perhaps from some of these early adopter regions as the technology is starting to spread to other ISOs?
Well, I think as you can tell about the deployment of storage in markets like California and Texas, as you bring in more and more renewable capacity, you want the firm power, right? Dispatchable power to a certain extent. And as renewables grow in scale, and that's likely happens. And at some point, the markets will demand it, the regulators will demand it. And in markets where you have a regulatory structure and a policy framework, like California, for example, they were driven by a policy framework. Okay, you shall deploy this amount of renewables and this amount of storage, okay? And that happened in that market. And that has been very supportive to bring in large amounts of renewables and storage to go with it. But if you take deregulated markets like Texas, similar story happened for different reasons, because they had significant amount of wind and significant bottlenecks as they brought up a lot more solar and wind, and they needed large amounts of storage. And storage became cost effective, and they got deployed, right? So in both markets, one is regulated market and a fully deregulated market, which is primarily driven by real-time pricing. Things happen similarly, and that's a good sign, which means the technology is at scale to be deployed. That's where we are.
Okay, so we've talked a lot about sort of the macro transmission level integration, but are there limitations at sort of the distribution level, and how do those challenges maybe, how are those compared to these macro scale challenges?
Sure. Well, if you think about distribution network, one of the major characteristics is, well, they are traditionally designed for single directional power flow, right? So power flow from substations through distribution lines to the end customers. Even though the adoption of distributed solar change this picture a little bit, but depending on where you are, how much solar penetration you have, which utility company you have, a large part of the distribution grid, you still expect this single direction power flow paradigm. And now you start to think about putting a bunch of distributed battery into the power network, and some of them are not small. Right, so you may inject a large amount of power back to the grid, and then the utility company have to worry about how do you enforce the physical reliability, constraints, voltage, power factors, and all these sort of things in the real time. Otherwise, you are going to have more blackouts, right? So that require observability of the distribution grid, which is lacking for a lot of utility company, real-time observability and controllability. Obviously, if you say actually the battery is owned by the utility company, so in that case, maybe they can control this battery. But a lot of distribution system batteries also owned behind meter by, for example, commercial industrial electricity users. In those cases, controllability and information sharing and incentive, all of them, they are questions that we have to address. So yeah, I would say, really how do we enforce the physical constraint with more observability, controllability, and setting up the right program to do this? I think that's the main challenge.
Great. And so there's also, energy storage is also an important technology for building grid resilience in the event of different outages. And so I want to talk a bit about how storage systems can be designed specifically to serve those kinds of systems and those kinds of outcomes. And so I guess, Professor Chin, what role do you sort of see electric vehicles or some of these other distributed energy resources playing in that design?
Sure. I work on power systems. So as a power system researcher, the way that I think about electric vehicle, they are really just battery on wheels. And there are a number of statistics support that. For example, normal or average consumer vehicle, they are parked 95% of the time. And if you have all this as EVs and the batteries sitting there, if there's a way for us to utilize them for the grid purpose, that would be great for someone like me who work on power system, right? So the question is really, okay, number one, how would you be able to do that? Again, you get into issues about whether people have incentive to do that and how do you set up the right coordination scheme. But in terms of potential, there are a lot of potential. For example, our group, we have a recent paper just trying to quantify the entire EV fleet in the city of Chicago. If you can sort of coordinate when and where charging happens, still, people still travel, but use the EV the way they are using today, that's equivalent to an order of hundreds of megawatt hour of stationary battery. So we can sort of come up with the equivalent stationary battery capacity based on the flexibility you can derive from EV. And that by itself, we are simply sort of coordinating when charging happens. So it's only charging. Now, if you think about the possibility that you can also discharge your EV battery, they are bidirectional chargers and doing so-called vehicle-to-grid application, you enable other applications. For example, you may have a blackout in your house and you have an electric vehicle. Potentially, you can use your EV to provide backup power to your house. That sort of thing is really, really useful in a resilience context where you have extreme weather events and so on.
And so I guess sort of building on what was in the lecture, Professor Pohl, what gaps exist in battery chemistries, especially for these longer duration applications, or maybe at some of these more distributed levels?
Yeah, so the lithium-ion batteries can store charge rapidly and give you back rapidly. But for the long duration, lithium-ion may not be the technology that you should be using. So for example, flow batteries could do that very well. Iron flow batteries, vanadium oxide flow batteries. And they are much more abundant and inexpensive to produce. For example, iron is 200 billion tons in the world. However, lithium is only 100 million tons. So there is pros and cons, which technology you are going to use and how we can suffice. So for the grid storage, there is a huge amount of need. Lots of batteries are needed. So more the technologies we are going to come up with. For example, there is alternative sodium-ion batteries. Sodium is abundant everywhere. Those technologies can come up and store also energy and give back whenever you need. But again, sodium also will give you power rapidly compared to all other aqueous systems.
And I guess sort of building on that, if you're thinking about integrating some of these newer technologies, how do you value sort of the benefits of resilience compared to sort of other rate-based incentives for energy storage and other generation technologies?
Sure, yeah, and so there's a couple of different ways of looking at this. So I mentioned earlier there's sort of a number of different markets and products that we administer at wholesale. So early on in places like Texas, you got a lot of value from ancillary services. So those are products that are used to manage the grid at really short time scales. That's been shifting as those are kind of saturated in places like Texas to energy arbitrage. So you get some value from periods where demand is high and the energy price is really high, and periods when the price is lower. And so the difference between those high price periods and low price periods, a storage resource can capture that difference and make money off of that. In MISO, there's also kind of a third resource adequacy or capacity revenue stream that's pretty important, and we've been making a lot of changes to the way we look at resource adequacy. as the markets have shifted away from thermal dispatchable resources and more towards wind and solar and other less or not dispatchable resources. And as a part of that, we've been focusing on how much availability do we expect to see from different resource classes during the periods where we most need them. So not necessarily during the peak load period, which has traditionally been how we've planned for the resource need for the grid, but during periods where perhaps solar is coming offline, it's not as windy, maybe you're still in a relatively high, if not the highest demand hour. And so those periods of need, you expect storage resources to be available largely during those periods and to be able to then capture a pretty large share of the resource adequacy or capacity value. And that's what we've seen. And we've also seen that longer durations can capture more of that value up to a point. And this is, a piece that I've been thinking a fair bit about. Is like, what is the sort of duration saturation for the current configuration of the grid? And what we've seen is it's a little bit more than 4 hours, but certainly not out to 100 hours. And so there is a question in my mind about how much duration is valued given how the grid looks today.
And so then, Professor Chalamala, what sort of partnerships between, whether it's utilities, whether it's the PUCs, tech companies, regulators of other types are needed to be able to unlock sort of these next generation grid storage technologies compared to where we're at today?
Well, I think, there is a role for engineers to talk with the regulators, okay? That is the key. Regulators tend to be lawyers. So they're not technologists. So there is a role for us to bring what technologies are, what they can do, and provide the level of knowledge base that they need as they develop their policies. Because policies have to be developed with some level of technical knowledge. What systems can do, what is the right technology, and what are the things that can be implemented at scale. And as they develop the regulatory framework, is the decision-making is based on known data sets. So there is a serious role for us to engage. Okay? That's one thing. And that, for example, in my case, when I work for Sandia, we always talk with PUCs. So we actually hosted day-long or sometimes week-long workshops to bring them on board what all these different technologies are. So that process, we need it, okay? There's also a place where we as engineers need to talk with the regulators because, to develop or make standards implementable in a regulatory framework, they need to have a role. And that's, again, another role that we can play.
And so then the next topic I wanted to talk about, sort of the elephant in the room whenever you're talking about grid planning these days, is what do you do with data centers? How do you manage this potential growth? And it's taking off at a really rapid rate. Nobody's been able to predict whether it's a bubble, whether it's not a bubble. And so maybe how are you thinking about it sort of as the transmission level operator, thinking about planning extra either generation or transmission capacity and where to locate those resources?
Yeah, so that certainly is a very big topic at the moment for us and others. So we have, just for context, we have about a 122 gigawatt peak system in MISO. So that was last year. In 2013, we also had 122 gigawatt peak system. So the load was totally flat, right, over the last more than decade. And now when we look out to 2030, it looks like anywhere from 8 up to 25 gigawatts of growth on top of that is, we're trying to be credible with these numbers, right? It's very difficult to get an exact number, but that is kind of a reasonable guess based on what's coming into our variety of processes. One of the things we've done in the last year or so is try to introduce an expedited process for getting generation connected to meet some of that load growth. And a significant chunk of that, not all of it, and not actually the majority, but a significant chunk is coming from storage. So that's part of that 10 gigawatts of incremental growth that I was talking about. So there is this wholesale storage play, right? I can get capacity, I can get some energy value and serve some of that load with storage. So that's a part of it. The other thing, and this has come up earlier, is some of these large loads will have on-site storage to serve as some sort of a backup. And there's this kind of open question of how interested is that storage in providing broader services to the grid, or is it really just there to provide local backup?
Great. And I guess sort of building on that, Dr. Pohl, are there sort of different battery chemistries or types of batteries that are more well suited for those data center applications? Are you seeing different sort of electrochemical technologies for them versus other sort of industrial consumers or grid applications?
Sure. So in batteries, there are different battery chemistry within lithium-ion batteries. So for example, some of the batteries can give you rapid power. Whenever you need the power or electricity, it is readily available. So lithium iron phosphate is one of the cathode that can give you power very rapidly, which is also inexpensive and also safer cathode among all other cathode, NMC-based cathode, where nickel, manganese, cobalt is utilized. So lithium iron phosphate-based cathode, they are cheap, they are safer, and also give you power rapidly. So the data center point of view, they are the kingmaker, or they are the king of the batteries today to utilize. So if you need rapid power, lithium iron phosphate electrochemistry is a winning thing.
And so, Professor Chin, are there challenges? Is there competition for the load growth, right? So for some of these distributed energy resources that you work with versus the data centers? Are there people that are winning in sort of the competition to get connected to the grid? And how do you manage those kinds of challenges in your work?
Sure. Well, theoretically speaking, if you think about data center loads, they are loads to the grid. If you think about EV charging loads, they are loads for the grid. And if we are sort of in a scenario that, it takes years for you to upgrade the grid capacity and do the expansion, and this load have to wait for a very long time, and they don't want to wait, in some sense, there's some competition, maybe, for area with a lot of data centers sitting in the interconnection queue, it might be a little bit hard for you to connect a very large EV charger, hypothetically speaking. But of course, the data center load scale and the EV charging, even for larger ones, they're quite different. So potentially for data center, you may have to directly talk with the system operator for the transmission grid. And while for EV charging a lot of time, as long as the utility company is okay, you can satisfy the grid constraint for the distribution network, everything is fine, right? So in that sense, perhaps this competition is not that fierce in some aspect. But then there is also, I would say, some sort of synergy in the sense that, these days, all this attention that has been attracted to this topic of data center interconnection, right? So, government is interested in this, all the system operators, and I think recently DOE sent a letter to FERC. All this attention, as well as attention from the research community, we're sort of trying to push the frontier of, how do you sort of speed up the process? What are the technical problems to be addressed? What are the administrative sort of procedure that you may streamline? So all these sort of things, it's not only beneficial for data center, but also potentially beneficial for other large loads. So in that sense, there might be synergy or maybe, effort done for one type of load is also useful for another.
So Professor Chalamala, with AI data centers sort of projected to be this huge power consumers, do you expect storage to make up a lot of this new capacity on the grid? Are there other technologies that might be further incentivized sort of alongside the storage, and how would that potentially influence sort of the grid deployment based on the trends you had shown before?
Well, let me point out where things are with the data centers. I mean, if you look at the data center operators, where the new capacity is coming online, it's primarily, on-site generation of natural gas. That's what they're building, right? And would storage make a difference? You have to think about where storage plays. Right now, all the data centers have UPS as part of their architecture, and that's for power quality for the most part. It's not an energy storage device. So you don't really bring energy storage in behind the meter in a data center at this point. And that's primarily they're worried about safety of lithium batteries. So lithium batteries are not inside the data centers. So the question is, can we bring few hours of energy storage into the data centers? That way we can take the loads to be not as peaky or lumpy. And that, I think, a lot of the companies are driving that right now. Can we bring in few hours of storage into the data center infrastructure so that I don't need a gigawatt capacity? I can live with maybe 500 megawatts, right? Do I have enough 1, 2, 3 hour storage that provides and take away the lumpiness, take away the peaks? So that's where I think the storage is coming. And is it coming yet? I think, companies who are building the operations or the infrastructure companies and those who are in the UPS business, like Schneider and others, they're all actively looking, how can I optimize? How can I actually bring energy storage into in the infrastructure so that I can take away the need for large loads?
Great. I think that was most of the prepared questions, but if there are questions from the audience, I think we're happy to take those. At this point, just wait for a microphone from somebody so that there's people who might be able to see stuff online.
My name is Jackie, and this is for the MISOs. I was wondering how you guys are planning to handle the large load oscillations from the AI data centers. Do you guys write specific grid code requirements requiring it? Because I know like other ISOs are basically trying to say, hey, this is the voltage and frequency that you guys must meet. This way that the cost isn't on the community itself, but instead the cost goes directly to the data centers. So what is MISO's plan in terms of designing some sort of interconnect requirements for that?
It's a good question. And I'll separate out the cost from the kind of interconnection reliability piece, and we'll see how satisfying you find this answer. So coming back to what Prabhu was saying, the way that we organize the electricity system in this country is fairly complicated. And in particular, one of the cleavage points is around who is responsible for the load. And traditionally, the answer to that question has been the states have authority over load interconnection. And so if you look at MISO's processes, they're very asymmetric on the generation and load side. So we mentioned the IEEE 2800 standard, which established frequency and voltage operating ranges, fault ride-through characteristics, and we were able to implement that for generation connecting to our grid. We don't have a place in our construct to establish something like that for loads. So what we're doing right now is we're talking to the people who are our members, who are our state jurisdictional utilities, and have things like grid codes to establish requirements for their loads. As the industry catches up to this, there's lots of discussion happening at places like NERC, ESIG, EPRI, around just what those requirements should be and how to establish them in a way that is going to maintain reliability but not prohibit investment. There may be some shifts in that, right? And there's kind of a discussion at the federal level about whether entities like MISO should take a bigger role. But right now we're kind of leaning into our partnership model and working with our members on that topic. On the cost side, this is something also where most of the sort of tariff and rate making action to protect customers from the cost of large loads is again happening at the state level. So where this mostly hits in MISO's construct is on the generation capacity and transmission side. And in both places, we have ways to make sure that the costs are allocated back at least to the utility, who can then sort of do with that whatever their state requires, hopefully protecting their retail customers from cost shifting.
The focus of the panel has been on storage. There is another part of the equation, efficiency in transmission, in distribution. how important does the panel feel, putting a lot of emphasis also in making transformers, transmission lines, far more efficient than they are today in order to mitigate the desperate need to produce more energy?
Well, I think, that's a good point. We tend to not look at the efficiency aspects. I mean, large transformers are very efficient. So the question is, can we bring the new assets to be as efficient, right? We have learned to make the transformers to be super efficient to the most part, right? And now if I have a storage device which is, let's say, flow batteries, 70% efficiency is a good number, right? Can I afford to live with 30% inefficiencies on a larger scale? That's a problem, right? And I think, that applies for everything that we are doing, all the different assets from data centers to everywhere else where we have large loads. Do we have the same level of efficiencies that we are used for in the electrical system? The answer is no.
Yeah, lithium-ion batteries will give you 99+% efficiency, but they are not enough. They are not available readily. So that there is pros and cons with lithium-ion technology to be utilized for the grid storage or microgrid storage. And other batteries, including lead-acid batteries, 75% efficient only. Other new technologies are also not very efficient, including solid-state or new other technologies, lithium sulfur. So they have own problems. So we have to deal with whatever we have in the storage community, that's lithium-ion battery with 99% efficiency. But even in the grid, we also lose a lot of energy transmitting it. So we also have to think about how much we lose with the whole structure of the grid.
Yeah, just one other comment on that. I mean, I think the efficiency point is important, but also, so that's coupled with the value. Like, there's lots of places where there's energy losses in the wholesale electricity system and elsewhere, right? I mean, I think an efficient gas combined cycle is only 40-ish% efficient, right, in converting the thermal energy to electricity. So we put up with that because it's still justified, like it's still cost effective. And I think coming back to the use cases, it's more about finding those opportunities where you can deploy storage effectively, even though the efficiency is never going to be perfect.
So if I may add something from the grid perspective, grid is really just about you want to make sure that when people need energy, you have energy at the right time and right place, right? So, a lot of the thing like Dia mentioned, it's about use cases. And for different use cases, we typically look into different options, what are the options that's available, and according to that use case, make a decision about which of the technology we're going to adopt and so on. So I don't really think this is like a universal answer in terms of, okay, maybe this technology perhaps is more efficient, but there are other dimensions in this technology. Maybe that's more costly, maybe that take larger space. So for certain use case, perhaps it does not make sense, or it's make more sense for you to use a less efficient technology.
And I guess one other data point on this, right? So if you have 80% round-trip efficiency technology, which I'm not a battery technologist, but something like a lithium-ion, right? You only need a 20% difference in the value of energy between two intervals in order to recover that loss, right? Whereas we have intervals where the price of electricity is 0, and we have other intervals where the price of electricity is $10,000, right? So in principle, there's more than enough volatility in that price to recover the cost of the losses. You just have to be careful about how you operate your asset.
Thanks all for your insights. It's been a really interesting discussion. A lot of the discussion has focused on sort of large-scale battery energy storage, except for a little bit, Junjie sort of hinted at the fact that more and more devices, including electric vehicles, but also other things like stoves and air conditioners and so forth, are now having batteries sort of integrated into them because the cost is now so affordable. So DL, I wonder if you could talk about in MISO specifically, is there a pathway toward aggregations of distributed batteries, being able to sort of play either in ancillary service, energy, or capacity markets? And then, I don't know, if anybody else wants to weigh in on sort of what that looks like in other markets and maybe kind of what the best practices or the ideal would be there.
Yes. So the answer is yes. The Federal Energy Regulatory Commission's Order 2222 had some prescriptions around that, right? So we are working on our compliance, which includes distributed energy resource aggregations and an implementation of that kind of on the next 5-year time frame. It is fairly complicated for a variety of reasons, and one, that we'll register with some of the panelists and others is that the individual components of the aggregation can be in different locations on the grid. So how do you manage flows and congestion in that context? So there are some bounds, and then there's some technology that needs to be implemented in order to support that. And we're working through that process right now. So we do expect to see some of that. Yeah.
What do you feel like, in your experience, what are the best markets on that? The most advanced markets for integrating kind of aggregations of distributed batteries? Or Junjie, feel free to comment too.
I mean, there is an effort to, aggregate things. And aggregation is happening at a pretty small scale, right? Because operationally, how much capacity do you have to bid into? 30 megawatts, 50 megawatts, 100 megawatts, right? So it's a size issue. So there are companies that have done that over the years to aggregate. I think it's an evolving thing. So there is no technical barriers to participate in several of the markets at this point. It is more about, can you do it? Can you effectively do it? And is there a value that somebody can derive that we can sell as a product? That's where the things are. And then people keep asking about, aggregation of or capacity available from electric vehicles and other things. Those are technically behind the meter assets. How do they participate is still a challenge. And how do you use all these assets as grid assets? We use them in many ways. We talk about they being available as resilience assets, but none of them are grid forming. They're always grid following, right? So people are looking at how do you make things grid forming. That's when the participation can increase significantly, and that part is, I think, grid forming standards and making the assets grid forming. That's just starting now. So because if you want to really participate, then you need to be available to the grid anytime.
Just building upon Babu's point, I don't really think there's a technology issue. But there are a lot of business issue in the sense that, okay, you have all these devices, they are sort of built by a different manufacturer, and they may or may not open up the API for you, for a third-party company to do the sort of things, right? I think one of the most successful example of the sort of battery aggregation is Tesla, where Tesla have their batteries, their EVs, and in Texas, it's relatively easy for them to go through this entire business ecosystem because they have direct access to different assets. So with that, I think they got some quite significant capacity as a virtual power plants, and they are able to participate in different system operators markets. So in terms of access or API, and in terms of the sort of incentive, I think incentive is another issue because if you are going to utilize in a way that customer are going to recognize, and they might if you charge or discharge their battery in a way to that negatively impact their normal usage of their devices or their appliance, they might complain. In that case, you have to pay them. And the question will be, okay, how does this incentive set up? Or potentially you are going to provide an opt-out possibility, right? If the customer do not like it, they may just switch to their normal usage, and that translates to a reliability issue, right? So maybe at their high market, you come up with this calculation, the aggregator figure out, okay, maybe I'm going to be able to bid this capacity, but 30% of customer opt out because maybe you have a very hot day, right? So I think those are the challenges essentially we have to address in some way.
On the topic of Tesla, what do you have to say as for different high energy consumption states such as Illinois, California, and Texas partnering with companies like Tesla or Sunrun in order to incorporate more residential solar and battery virtual energy grids throughout these states? How do you see that puzzle piece fitting into the overall challenges and opportunities we see going forward as we need more power for these data centers?
Sure. So the way that I think about this, I myself, in terms of my research, I work a lot on the demand side, in the sense that I'm really trying to figure out, there are all these challenges about how would you be able to incentivize the demand, so demand somehow follow some signal from the grid. That can be price, can be direct control signal, whatever it is, or maybe indirectly through some aggregator. For example, in this case, Tesla might be playing a role of an aggregator, right? So I think that's beneficial. Definitely, it's a resource. It's out there in the sense that comparing to, let's say you have to go there and build a new power plant, or maybe like build new energy storage plants. Maybe it's more cost effective because this resource is already out there. What's missing is really the control and the incentive and all that sort of software per se, right? So, but making the software right, I think that's still something that we have to figure out. Tesla have done some job in terms of, at least within their ecosystem, they are able to do this. But a lot of time it's not just about Tesla, it's really about all the other company, all different type of resources that's out there. How would we potentially integrate and aggregate them and potentially participate in, let's say, wholesale electricity market, the MISO market?
Yeah, it's a good point. You can have your small grid kind of thing where you have a solar panel, you have your own batteries, you generate the electricity, store it, and utilize it. But more complicated thing is you also sometimes do not have enough energy produced yourself, so you have to get it from the grid. And if you produce excess, you have to send it back to the grid. That integration is not happening locally to your houses and buildings. That should be happening in near future. So that integration is very important when you generate excess, what to do with that. And if you do not have enough, then you should have access to the grid. So it should be really happening time to time, or almost in near future. It is going to be more important to have a small microgrid, local energy harvesting and storage kind of business.
I think, if you look at from a cost performance point of view, right? Utility scale always beats you. So that's why we build large plants. I mean, 500 megawatt plants are pretty common now, right? That's one. The other thing you have to think about is most people live in dense urban areas. You don't have the rooftops available for the energy needs that you have. So we tend to build plants where you have availability of land on a large scale and bring that transmission capacity to sustain the cities. I mean, look at New York City. I mean, where do you have renewable energy in New York City? You don't, right? So you have to bring it from somewhere else. And building larger plants is more economical, right? And we will ultimately, we have to learn how we are not going to be untethered from the bulk grid. Bulk grid is going to be there. Okay, how do you bring the capacity that you need for all the needs that we have?
And I guess the only thing to add from my perspective is that kind of as the operator of that entity that can be leaned on if you have excess or you're short, right? We can kind of stitch together a bunch of different state or local areas that have quite different policy goals. So in our footprint, we have Illinois that you pointed out, and we also have Louisiana, quite different policy kind of approaches in those states. And the amazing thing is that you can actually integrate states that are that different into one regional footprint and one market and make it all work. There are some challenges that sometimes arise around, making sure that solar farm that is incentivized by state policy can realize its value in the wholesale market, or that local behind the meter resource is able to participate, so you can kind of line up the value streams. And we spend a lot of time thinking about those gaps where they occur, or visibility, making sure we have enough visibility into how those resources are behaving. But most of the time, it actually works pretty well.
I think we have time for one more brief question.
So, with the increasing demand for power from these databases, do you imagine that there would be an increase in the number of nuclear power plants being built? And if so, or if an increasing amount of the grid's electricity is produced by nuclear plants, what challenges does that entail?
Yeah, so it's a good question. And what we've seen recently is not so much new nuclear construction, but reactivations of nuclear units, sometimes individual units that have been retired or mothballed, sometimes stimulated directly by a large load who's interested in contracting for that power. So that's kind of the first wave. There's also a lot of discussion around kind of a new wave of nuclear technology that's a little bit smaller, a little bit more modularized, and ideally a little bit lower cost, kind of paralleling the conversation we've been having about storage. That technology is pretty early in its deployment, earlier than certainly lithium-ion storage is. So it's kind of at the pilot stage. So there are small modular reactor projects that are happening, but they tend to be happening in jurisdictions that have more kind of government oversight and protection, so that you don't have a private capital that's at risk today. And it looks like it will probably, I mean, optimistically take maybe 10 years for that technology to mature and be available kind of commercially. So I will say, yeah, it does sound like there's interest in this space, but it's not something that's going to happen overnight.
All right, I think we can leave it there. I would like to thank all of you for being here, and we can get a round of applause for our panelists. Thank you so much.
Thank you.